Good day, everybody. My name is Rolf Mostert, and I'm going to tell you about a project that my colleagues and I undertook. We are from the University of Pretoria in South Africa. Our talk has to do with the work that we did on high temperature hydrogen attack, also referred to as HTHA. We developed equations which can be used to describe the process of HTHA degradation, and we'll show you how we think these equations can be used to enhance structural integrity assessments. This slide explains why we did the work. The traditional way to manage HTHA is via these Nelson curves. These are the 1967 Nelson curves for carbon steel, carbon half moly, and 1 chrome half moly steels. These lines are based on industry experience only. If you operate below the line, it was believed that you'll be safe, and above the lines unsafe. The problem is that over time industry experience shifted and the lines with it. These are the 2016 Nelson curves. Here we still have the carbon steel curves, although they have moved to lower values. And the next curve is the 1 chrome half moly steel curve. What is missing is the carbon half moly steel curves. This is due to increasing uncertainty about the HTHA performance of these alloys. Now, if you have a process unit constructed from carbon half moly, earlier, and it's operating at 700 Fahrenheit and 600 psi, you would have been quite satisfied and confident before 2016 about its structural integrity, but not so now. Many units now operate above the Nelson curves. The consequence is that the probability of failure is uncertain, but the consequence of failure is potentially very high due to the presence of flammable hydrogen. A new approach regarding structural integrity assessment is clearly needed. New assessment methodologies are currently being developed, such as those contained in the new draft WRC 585 and 586 bulletins. Our work is aimed at contributing to these new methodologies. We formulated two goals for this study. We wanted to describe the kinetics of the HTHA damage process mathematically for carbon and carbon half moly steels and welds. Thereafter, we wanted to establish how such a model could assist in improving the structural integrity assessment of units fabricated from such steels. The steel we used was a typical carbon half moly steel as shown. The heat treatment was normalized and tempered, and a weldment was investigated. This was a production test plate from a weld qualification procedure. Smaller samples with the dimensions given were sectioned from the weld using EDM, as well as from the has and base metal. The samples were fastened in a jig, and the high temperature strain gauge was then welded onto the samples using precision capacitance discharge spot welding. The strain gauge assembly was checked thereafter in uniaxial tension against a calibrated extensometer and load cell as shown here. An excellent one-to-one behavior was observed. The sample instrumented with a strain gauge was then inserted into an autoclave setup as shown here, pressurized with hydrogen and exposed. We supplemented our results by analyzing published strain life HTHA curves by others, such as the carbon steel curve shown here. The published curves were digitized and subjected to mathematical analysis. The mathematical analysis showed that the sigmoidal equation best describes the strain life HTHA behavior for all steels and microstructures evaluated. The equation uses four constants as shown. A1 and A2 are the intersection and projection onto the y-axis of the plateau, respectively, while dx is the hill slope constant. The strain rate versus time curves show a rapidly increasing strain rate, which similarly retards beyond the peak value. The x value corresponding to the peak is the x0 constant in the equation used. For the carbon half-moly steels, the strain versus time plots were significantly slower than that for the carbon steel. This is the curve for the Has sample. The x0 value, which is the inflection point here, for example, is 366 hours, which is about 20 times slower than that for the carbon steel. The microstructure of the steel after completion of the run is shown here. The microstructural damage was relatively evenly distributed along the prior austenite grain boundaries, and a strong anisotropy was not present. In the base metal sample, for instance, strong anisotropy of the HTHA damage was observed due to banding being present in the plate material. Generally, it is understood that the cause of HTH damage progress is the methane pressure that builds up in cavities. The process of cavity growth and coalescence is therefore believed to be closely linked to the process of creep. And creep is currently adequately described by the MPC omega method, which makes use of the concept of a damage fraction. As the creep damage progresses with the passage of time, the damage fraction progresses from 0 to 1.0. This principle was applied to the HTHA strain time curves developed for the carbon half-moly weld zones. The result normalizes the three weld zone damage results and allows direct comparison of the three zones of the weldment. The resulting sigmoidal equation is also now simplified, with only two constants, alpha and beta, required to describe the behavior. The comparison of the damage rates of the various zones provide insights which are important for both quantitative and qualitative management of the HTHA damage process. The comparison shows that the damage processes start slowly for the weld metal and the base metal as time increases, where the damage rate remains constant for a period for the Has, whereafter the damage rate starts to accelerate. For all zones, the damage rate rises to a peak value, whereafter it decelerates. We now come to the section where we discuss the application of this work. First, we'll focus on where the work can contribute to calculating future HTHA damage. It has been shown before that creep behavior in a hydrogen environment is much more rapid than that in air. Compare, for instance, the creep behavior of 100 MPa applied stress in air to the creep behavior in hydrogen at the same applied stress. This observation has led to the realization that the creep acceleration due to hydrogen could be quantified. In this case, it could be equated to a stress increase of 40 megapascal, because a creep curve in air at 140 MPa, as shown, is very similar to a hydrogen creep curve at 100 MPa. It was recently established by the WRC that the additional stress is directly proportional to the pressure of the methane caught up in the cavities, according to this equation provided. The alpha parameter provided here is called the methane proportionality parameter, and it is fundamental to the assessment of HTHA life. The test rig used by Mana was quite sophisticated and elaborate to obtain the required strain measurements and at the same time maintain hydrogen safety. If the alpha parameter is known and accurate, the magnitude of the methane stress, the delta sigma, can be calculated. The methane pressure for given conditions and time is known. So if the delta sigma or the effective methane stress is known, accurate life assessments can be carried out. This table shows some upper bound values for alpha established to date. Due to the intricate experimental setup, only a limited amount of information is available about alpha values. The alpha parameter has been referred to as the material dependent parameter, and it appears that it may be dependent on stress, temperature, and probably microstructure. It is proposed that the alpha parameter can be established using the HTHA setup shown in this work or similar. Considering the damage curve for the base metal carbon half moly steel shown here, it is found that the time for reaching a damage fraction of 1 is in the order of 480 hours. One can then calculate the equivalent applied stress that will also arrive at the same damage fraction through creep using the API 579 omega methodology, and the result is in the order of 450 MPa. This stress value is high, but you do get these high stress values in HTHA studies. The equivalent methane pressure, for instance, for these exposure conditions and steel has been established as being in the order of 483 megapascal, with the consequence that the alpha value is calculated as being 0.93, which is in keeping with the value of 1 shown in the previous table. The benefits of alpha values established in this fashion are summarized here, as well as some of the uncertainties and further work that still need to be done. The second application of the current work has to do with tracking the HTHA damage process by attaching high temperature strain gauges to structural members that need to be monitored. The evolution of HTHA strain can then be tracked in real time. The difficulty is then to know what the strain values found means in terms of structural integrity. Here we show the sigmoidal strain life curve for carbon steel and its first, second, and third order derivatives. The third derivative curve splits the full HTHA cycle into 4 regions. Comparing the third derivative assessment points A and B against the full life cycle for argument shows that point A falls within the first phase of degradation and point B in the second. Of course, further work is needed to determine what the 4 phases mean in terms of mechanical property degradation and cracking. We therefore conclude that the application of encapsulated strain gauges to lab samples in an autoclave and to structural members can be used to experimentally determine the methane proportionality factor alpha for surface-exposed samples in various microstructural states, facilitating accurate HTHA assessments using the WRC 585-586 methodologies. And secondly, monitor the structural integrity of process unit members with a view to establish its stage in the HTHA degradation process. Thank you very much.